Why Mandelbrot? This is the second in a series of videos that asks the question, why Mandelbrot? In the chapter 1, we talked about the secret sauce. And in chapter 2, we're going to be talking about complex variables. If you remember from chapter 1, we talked about the recursive equation that Mandelbrot used in order to create his beautiful graphics. And we talked a lot about it and how to use it, but we didn't talk too much about what C was. Well, we're here to say that C is a complex number. It's represented by A plus BI, where A is the real component and BI is the imaginary component. And let's talk just a moment about square roots. We know the square root of 4 is 2, because 2 times 2 is 4. We know that the square root of 3 is a very long number. We know the square root of 2, 1.414, etc. Square root of 1 is 1, because 1 times 1 is 1. Square root of 0 is 0, because 0 times 0 is 0. And the square root of 1 is I, because I times I is equal to -1, which is the very heart and soul of complex numbers. We have to accept this property. I squared is equal to -1. And I need to point out here that just because it's called imaginary, it does not mean that this subject doesn't exist, or it's imaginary, or it's unimportant. Just the contrary. It's extremely important and it's very real. And it just happened to be named imaginary because it didn't fit in with our normal real number systems. Let's see if we can prove that I is equal to the square root of -1. Well, one thing we can do to prove it is, as long as we maintain the balance of the equal sign, we can multiply both sides by 3. So 3 times I and 3 times the square root of -1. This is equivalent to this statement because we haven't unbalanced it. And likewise, we can square both sides and still remain balanced. We can square 3 to 9, square I to I squared, 3 to 9, and we can square the square root of -1 and make it -1. And at the bottom line, we know that -9 is in fact equal to -9. So that does show that this statement up here is accurate, and we will claim a QED on this one, which is we demonstrated that what had to be proven. Now for some definitions. This sentence, basically this paragraph, came from Complex Variables by W.P. Novinger. And what it says basically is if you use an Argand diagram, and if you set this point here to be equal to I, then we can talk about the rest here. So let's talk about this just a second. 0, 1 means that there's 0 on this axis and 1 up this axis. And that we have to equate that to the imaginary number I, if we're going to make this an Argand diagram. Just like if we had a real number A, this would be A, 0, and this would be the intersection of A, with a B. So this would be A, B. So what the definition says that if you do that, and the real number A is identified as A, 0, then this point, A, B, can be represented by the complex number A plus BI. Now this expression A plus BI can be manipulated as if it were an ordinary binomial expression of real numbers, subject to the relation I squared is equal to -1. Now let me say what that means. That means that we can treat this as a normal binomial. We can treat it as an ordinary binomial expression and apply all the rules of algebra that you have learned for years, and nothing will be changed except for when it comes to I squared. We have to bow to this fact if we're going to treat these as ordinary binomial expressions. This looks like a busy slide, but we'll take it slow. Let's start with the fact that we're adding complex variables. We are actually adding this plus this, or this plus this. And we're going to find out what that means. Let's start with this diagram right here. If you notice that this point here is the intersection of the real number a and the imaginary component b. So it gives you a comma b. It also gives you a plus bi based on our definitions earlier. Just like this real number c and this imaginary component d gives you c comma d, or the complex number c plus di. Now the question here is, what happens when we add basically this vector to this vector? What happens when we add these 2 points together? Up here, let's just break this down. We know that a comma b is a plus bi, and we know that cd is c plus di. And then all we need to do is, based on normal algebraic associations, we can associate a and c together, and we can associate b and d together and pull the I off to the side. So our new point becomes quantity a plus c quantity plus quantity b plus d quantity I. Now graphically what that means is, if you add this vector to this vector, you get this vector, which is a sum of this length, and basically the direction somewhere right in the middle of those 2 vectors. What do we have here? We have a plus c on the real line, which is the sum of the real number a, and the real number c. It's right here. It intersects with the sum of the imaginary component b and the imaginary component d added together. Gives you a point right here. So this point is a plus c comma b plus d, which can be written, as we know from earlier definitions, as a complex number, a plus c plus b plus di. So that is how we add complex variables. And keep in mind that we are operating as they were ordinary binomial expressions. If you haven't noticed already, that is what we're doing. In fact, we're doing that so much so that we are incorporating the old memory trigger FOIL, which we'll talk about later. In case you haven't heard that, we'll define what that is. But FOIL tells us the order of how to multiply. So in FOIL, if you're going to multiply these 2 together, FOIL says you multiply the first, F for first, this one times that one, and there it is. And then this one says the outside, so you multiply this times this, and you put it down there. This one says the inside, so you multiply this times this, and you put it there. And this one says the last, you multiply this times this, and you put it there. All right, so you got AC, and so you try to associate like items. You have some things with I's in them, so you pull them together. You pull AD together with BD, BC, and so now you have AD plus BCI, and then you have BDI squared, because when you multiply these 2 together, the i's multiplied becomes I squared, which is essentially -1, which causes this positive to turn to a negative. And so the bottom line is that when you multiply these 2 points together, you get this, which is in essence AC minus BD plus quantity AD plus BC quantity I. What that means graphically Here you have this vector, which is the AB vector, and the CD vector. Now we're not adding them like we did before. We're not adding those together. We're doing something different. We're doing the FOIL operations on ordinary binomial expressions. And this, what that means is that this point here is AC minus BD. That's the value of that point. And AC minus BD matches the imaginary components of AD plus BC into this point right here, which can be called AC minus BD and AD plus BC, which in fact, like we are trying to prove over here, is equal to quantity AC minus BD quantity plus quantity AD plus BC quantity I. So what have we done? We've added two complex numbers together. That's not a difficult task. And now we've just multiplied two complex numbers together. And the key on the little memory trigger here, of course, was FOIL: first, outside, inside, and last. Just a quick review. When you're adding, you don't use all of FOIL, you just the first and the last. So if you're going to add these, you add the first, this one and this one, comes to 3. You add the last, this one and this one, it comes to 4. So the sum of these 2 points is this point, and graphically, just like before, here it is. The sum of those two vectors is 3 plus 4i. Reviewing the multiplication of complex numbers, we're using FOIL. And FOIL says first, so the first we multiply 1 times 2. 1 times 2 is 2. Then we multiply the outsides, which is 1 times I. 1 times I is I. We multiply the insides, we multiply 3i times 2. 3i times 2 is 6i. Then we multiply the last, which is 3i times I. And of course, I times I is I squared, and I squared is -1, as you well know. We can put these things together, and the -1 makes this a negative, and the result is -1 plus 7i. If you notice, this vector is not leaning forward like the other example, and this has to do with the relationships between A and B and C and D. In this case, it happens to slope to the left, resulting in the quotient of those 2 points is -1 plus, excuse me, the product is -1 plus 7i. Again, we're treating this as ordinary binomial expressions. Okay, now we're going to put some of this stuff together, and it'll start to make sense, hopefully. Let's talk about this first. In Chapter 1, we talked about it, but I'll review it very simply, that inside Mandelbrot's universe, which is a circle of radius 2, there are points, and you pick a point when you start off the recursive formula, and then you give it to the recursive formula, and it computes its own internal points, and it keeps doing that over and over and over until there's a reason that it jumps this boundary, until there's a boundary test failure. I'll call that a border test. So the minute it crosses the border, everything halts. So if it passes, it stays in the circle, and it'll go on forever. If it fails the border test and the program has detected the fact that it's gone outside the circle of radius 2, it stops, everything's halted. So now look over here. Let's give an example. Let's say that this C is this point right here. What does the recursive formula do with this point? Well, here's the recursive formula. Excuse me for using the options here just for my convenience of x comma I, saying that's a function composed of those variables, a real and an imaginary component. So I take this basically Mandelbrot equation, I substitute this point. And so this gets substituted here, and this gets put here, and you square it. So you're squaring that function. Plus C. Well, what is C? Well, that's the one you just picked. So you put this over here and this over there. Now to square these, you go through the FOIL exercise like we just went through, and you come up that this is the answer of the square of those two binomial expressions. And we bring down C from upstairs, and then we do a little recombination, and we do a little addition and subtraction of these numbers, and the net result is another point. Just like here, it's like 0.2. Well, 0.2 is this. So the question is, and what the program does, is it does a border test on it. It's got a new point here. Does a border test. Has it passed the test? Yes, it has. Well, it takes this point and puts it up here in this position, runs down through this one again, and gets another point. Does a border test. As it passes, takes this point, puts it up here, feeds it into this Mandelbrot equation, and you compute a new point. You take the new point. It's a border test, pass or fail. And as long as it keeps passing, this recursion keeps occurring, and it'll go on forever. It'll go on forever. So that's why we need an upper limit. Like in the case of the ones that go on forever, as we said last chapter, we normally assign some large number like 1,000 or 10,000 or something like that. So that if something approaches those large numbers, we know that it's in basically an infinite loop and will never jump out. And we call it a set member. We color it black. So with the exception of that one breakout feature, the other way that this looping will stop is if there's a boundary violation. So let's try this again. You feed this one in. Let's say you feed this point, gets fed in here, and the recursive equation computes this point, which is out here, 0.6. Now it doesn't know, once it computed this point, it doesn't know whether it's valid or not. So it does a border test. Well, the border test will say it's well outside the circle, therefore it will fail. And what this recursive formula will do is say, I'm going to stop right here, and I'm going to count how many loops I went through this equation, and I'm going to report that out. And we'll see more about this later, but that's in general, from a high level, that's how it works. To go one step further and to help with our understanding of what's really going on inside the recursive equation, let's review Mandelbrot's universe. It consists of everything in the world is undefined except for his circle of radius 2. It's the only thing meaningful in Mandelbrot's universe. Outside the circle of radius 2 doesn't exist. Inside, we have three things. We have backgrounds, which is depicted by the white pixels. We have fractals, which are on the borderland between the white and the black. And we have set members, which are pure black pixels. So what we did in chapter 1, we picked 8 points and ran them through the recursive equation, and we found out how many loops that they went through. And based on how many loops that they went through, told us what they were. If it was 1,000 or over, it was a set member. If it's one of these, it's a fractal. It's one of these, it's a background. It's one of those, it's undefined. And we went through that. What we're going to be doing right now is we're going to be really looking at this just a little bit closer, and we're going to look at what's going on. These are run files right out of the recursive equation. You'll be able to see what's happening inside the recursive equation. These are various run files, one for each of these points that we picked. And we'll take these one at a time. So here we are. We'll get used to this particular presentation because there's quite a few of these, because all we're going to be doing is moving the point down, and we're going to see what happens. So we're going to start up here. The point is well outside the circle. It's out into the undefined area. We know that because the loop count came back as 0. And from chapter 1, we fed it in there, and we came back from the recursive function at a loop count of 0. And what we're going to do now is we're going to look at the run file 60, which records what happened when this was fed into the recursive formula. So here we go. It didn't go very far. It got fed into it. The recursive formula did a border test. The border test failed, and the loop count was reported out as 0, which is undefined, and so this point was rejected. It wasn't even looped. It was rejected. Now, before we go on to the next point, let's look a little closer at what this is all about. When you say border test, what you're really talking about is, are you outside the circle, right? In other words, you're either inside or outside the circle. Well, most of you might recall that the formula for a circle, if you're dealing with x's and z's as the variables, would be x squared plus z squared is equal to radius squared. Okay, that's the normal equation for a circle. So given any x and any z, you should be able to tell whether it's inside or outside a radius 2 circle. So here's radius 2, and radius 2 squared is 4. So the bottom line is, if you take this number and you take this number and you square each of those and add them together, and if it's less than or equal to 4, it's in the circle. Why? Because it's actually saying less than or equal to radius 2. Radius 2 squared is 4. So that's the border test right here. And this thing failed the border test because you took both those numbers, you squared them, and you added them together, and it came up to 4. Okay? Well, the border test, if it came up 4 exactly, it would pass. But it's over 4. It's 0.00129 over 4. So it failed the test. Let's go on to the next point. This point is just inside the background. And last time we fed it to the recursive function, it came out with a 1, which told us it was the background. Now we're going to go to the file 61, which is the run file, to see what happened inside this recursive function when we fed this point to it. All right, first thing it did, it took the point that we fed to it. First thing it did is do a border test on it. It goes, did it pass the border test? Well, 3.99, it is within 4, so it passed. Loop count 0 at this point. So in other words, this gave it the go-ahead to loop once. So it computes a new point inside the recursive equation. And it takes this new point and it does another border test because it doesn't know whether it's a good or bad point. Squares those two numbers, adds them together. It's 11. 11 is way, way outside the circle, so it failed. What does the recursive formula do? It says, I'm going to stop because you failed the border test, and I'm going to report out a loop count of 1. I'm going to report a loop count of 1 to the user. And we as the user would get the 1. It would say, oh, it's in the background. And that's how we know. Go to the next point. Okay, this point, we got a loop count of 40 coming back. This time it's not into the fractals yet, but it's really close to the fractals. It's still in the white border. When we fed it in last time, we came out with a count of 40. And now we're going to go look at the run file for the 40 loops of this particular point. So here it is. We fed that particular point, and the recursive formula kept generating points and kept doing border tests and kept generating points and kept doing border tests, recording the number of loops it had. Points, border test, points, border test. Every one of these passed. gets down to here, it comes down to this one right here. And it says I'm going to do a border test on 40. So it takes this number, he squares it, and this number, and squares it, adds them together, and it's 6. Well, 6 is greater than 4. It failed the test. So it's going to stop right there. It's going to report a loop count of 40 for this one, and report that to the user and complete that particular task. Now, just to show you one thing before we leave this, if let's say we are the recursive equation and we're trying to figure out what this point is, given this point. Well, how do you figure out 40 when you know 39, right? We know 39, it's this and this. So we plug those into the square here of this formula. We add C. Well, what is C? Well, that's that way up here. So we got this point plugged into the recursive formula plus C over here. And we square this with FOIL. Actually, yeah. So, and then we bring down C, we recombine, we come out with a new point. We have no idea whether this point is bad or good, but if you'll notice, it's really the same as this point here. It's a little different because these numbers were computed with a iPhone calculator, and these numbers were computed with a Dell mini series computer, mini tower, and probably way more accurate than the iPhone. But at any rate, they're close enough. You can see that this minus 1.47 and 2.15 are essentially the same as these, which failed the test. So we just confirm the fact, even though we computed this from scratch, we came up with the same result. Let's look at the next point. Now this one is got into the fractals. Now keep in mind this little cutout here is the same as this cutout right over here. So this is the portion of the baby that we're looking at. A little bit of the head here, a little portion of the upper body up here. So picking that point, we don't know what it is initially, so we feed it into the recursive formula. It comes back as a 41. All right, well, let's go look at the runtime files for the loop count of 41. So here we go, 1 all the way to 41 this time. Remember, it stopped last time at 40. This time it stopped at 41, did a border test and failed. Well, that's why it stopped. The border test failed. It reports out the number 41 to tell us that it is entered the fractal area. That's what the 41 tells us. You're now into the fractals. And so if you notice, all of these, here's C that we picked initially, all of these are green lights. They passed the border test, all of these, until it comes down to this one. Failed the border test, stopped the processing, and reported out a 41. Now, just like we did before, if we wanted to find out what the next point is, there's no reason to find the next point because we're done with this. But if we wanted to, we could plug these into this 42 would be utilizing 41. We could find out what that next point is, excuse me, and we could feed it into a border test by itself, and to come to find out it's 60. Well, 60 is well out of bounds, obviously. This 41 was 7, so the one next to it is way outside the circle. It's 60. So that is even worse than the one we stopped at before. I just did this so you could just see how the recursive function utilizes this formula to find out the next point. This time we're into the fractals. We're not into the body yet, but we've moved down the little nodule here. We fed that into the recursive function, came up with a 100 loop count. We're going to go to the runtime and see what that looks like. Here's our C up here, and since this is it's getting a little crowded over here, it's going to 50 and 75. These are all passing their border test, every one of these, except for it gets down to this one. And here's the border test. You take this number and you square it, and this number and you square it, and you come out with 6. Well, 6 is greater than 4. Failed the test. Reports out as a 41, which confirms that it is a fractal. And I've done a little bit of extra computation up here so you can see that what the recursive function did originally was took C right here, and to compute this number, it used this formula, and it put C over here, so it's got C here and C here, squared C and added C, came up with this number, which as you can see is a little off, because this was with an iPhone calculator and this is with a computer, but close enough for us to see that there is that's how this function is used. Okay, we got 500 on this one. We're getting real close to the set membership down here, right in the midst of the fractals. When we fed it in, we came up with a 500. We're going to now look and see what went on to get to that 500 loops in the runtime. So here we go. So here's C, and it's run. There's 40, 41 through 60. Now, obviously, we couldn't fit all of the 500 iterations on this one page, so we left off a number of different rows here and jumped right to the 480th one along with its point and let it run all the way down to 500. Well, guess what? Ran into 500 and failed the border test and reported out as a 500 fractal. Got some extra computation here if someone would like to follow along to how you get from here to there. Same process that we've been talking about. Let's go to the next one. All right, now we tried over here a little bit. This is getting real close to the black, but it's still a fractal. I know that because when we fed it into the recursive function, it came out as a 999, which is the highest you can get and not be a set member. So let's see what happened here. So we go 1 to 20. These are all border passes, border passes. We jumped here from 60 to 980 for obvious reasons. We couldn't put the whole thing on there. But we have the last part. It goes all the way down to 9999, and you guessed it, this failed the border test. Put some computation over here if someone would like to see how you can use a recursive formula for finding 43 if only thing you knew is 42. If the only thing you knew is 42, this is how to find 43. We're not going to go through it here, but it's there for your convenience. Next point. Oh, we got pay dirt. Look at this. We just got inside the black of that nodule, and when we fed that point in there, it came back 1,000. We knew we were in the black pixels. We knew that we had a set member, and now we're going to go look and see what that looks like within the recursive loop. So here we got from 1 to 20, 40, 60. Obviously, we couldn't fit all the stuff in, but if you jump to the last column, we got 980. And all the way down here, all the way down, it passed the 999 test, got down to 1,000, and guess what? I want you to notice this. It didn't fail the border test. It did not fail, but it stopped. Well, it stopped because we put a stopper on there. We said, if you're 1,000 or above, you're a set member. We don't want you to go up to an infinite loop and count forever. We want you to stop and tell us that it passed that upper test. So set members loop forever, only stop by the upper limit assigned to the recursive function. In this case, it was set to 1,000. We could have easily set that to 10,000, in which case we'd have 10,000 iterations, and it still would never have failed the border test. This completes Chapter 2 of Complex Variables of Y. Mandelbrot. We're going to continue on. We've talked about the secret sauce. We've talked about complex variables. Now we're going to get into the algorithm, which is basically primarily oriented if you want to do a software program on your own, to do your own graphics, or if you want to take a software program and implement it in your own way, changing your own parameters. These are the kinds of things we're going to be talking about here. When we get, and this won't be esoteric. It won't be just for a software guy. It'll be for the person that is really interested in this stuff and would like to do it on their own. And that we'll talk about how you can do it. It'll be a logical flow diagram, basically, and maybe a program, a simple program that you could even copy if you wanted to and execute it. So that's what that plan is for that. Then eventually we'll get into the monsters. These are These are the geometric shapes that are not nice to measure, are not nice to understand, that Mandelbrot brought to the forefront of mathematics. Shapes that were ignored for hundreds of years because they couldn't do anything with them, but Mandelbrot brought them forth. We'll talk about dimensions, and that is, there is another dimension to the Mandelbrot, and we'll talk about that. And of course, universal patterns, patterns that apply to all life forms throughout the universe, that are designated and designed by the work that Mandelbrot did.